3,000 horsepower, sitting completely still at 3 in the morning, running, no crew, no cargo, no movement, just a diesel locomotive alone in a rail yard, shaking the ground beneath it, burning fuel into the cold night air like it has somewhere urgent to be. And nobody, not the railroad, not the engineers, not the federal regulators, is trying to stop it. Most people who notice this assume it is negligence, a forgotten switch. Someone is being lazy. It is not. What is actually happening is a precise engineering decision made 100 times a night across every major rail network in the world. And once you understand the full picture, the physics, the costs, the cascading network consequences, you will never look at a parked locomotive the same way again. Let us start with the machine itself, because most people carry around a completely wrong mental image of what a locomotive actually is. A modern freight locomotive like an MD-SD 70 or a GE Evolution series weighs roughly 220 tons. That is heavier than a fully loaded Boeing 747 with passengers, cargo, and fuel on board. The diesel engine sitting at its core displaces more than 700 cubic inches per cylinder. There are 16 cylinders. The engine block alone, just the block, not the full rotating assembly, carries roughly the thermal mass of a cast iron skillet the size of a garden shed. It does not heat up quickly, and it does not cool down quickly. It holds temperature the way a stone wall holds the summer sun. Long after the source of heat is gone, the warmth stays locked deep in the metal. That thermal mass is important. Hold on to it. Now here's the thing about diesel engines that most people do not fully appreciate. They do not work like petrol engines. There is no spark plug, no ignition coil, no timed electrical fire. A diesel engine fires by squeezing air so hard that it superheats on compression alone, hot enough to ignite fuel the moment it is injected into the cylinder. That process depends entirely on heat already being present in the system. Cold metal means poor compression temperatures. Poor compression means incomplete combustion. Incomplete combustion means raw fuel washing cylinder walls, stripping oil film, and grinding down metal surfaces that cost tens of thousands of dollars to machine and replace. One cold start on a locomotive engine in freezing temperatures puts wear on internal components equivalent to roughly 800 miles of normal full load operation. Not a rough day, not unusual stress. 800 miles of accumulated wear before the train moves a single inch down the track. That is the first reason the engine never stops. Because starting it from cold is the most violent thing you can do to it. But the cold start problem is only part of this story. The real threat is what happens to the locomotive other critical systems when the engine goes silent in winter. Picture a freight locomotive sitting in a rail yard in Minot, North Dakota. January, minus 25 degrees Fahrenheit. The engine shuts off at 10 in the evening. By midnight, the coolant in the engine block starts losing temperature. By 2 in the morning, the coolant lines running to the radiators begin approaching freezing point. By 4, if the coolant mixture is not perfect, you do not have a locomotive anymore. You have a 220-ton sculpture of frozen pipe and cracked metal sitting in a yard with 30 other trains stacked up behind it. Coolant lines, fuel lines, air brake reservoirs, all of them vulnerable, all of them running through and around a machine that was engineered to operate, not to sit dormant in Arctic conditions with no heat source. And diesel fuel itself changes behavior in extreme cold. Below roughly minus 15 degrees Celsius, the paraffin wax that naturally occurs in diesel fuel begins to crystallize. The fuel thickens, gels, stops flowing cleanly through the injector lines. A locomotive that ran perfectly 12 hours ago simply will not start. Not because anything broke, because the fuel stopped being liquid. Here is the part that completely reframes the scale of the problem. The obvious solution, the one anyone who has owned a car in a cold climate will immediately suggest is a block heater. Plug it into shore power overnight. Keep the engine warm. Start it clean in the morning. Simple, obvious, logical. Except a block heater for a car is warming a roughly 200-kilogram engine block. A locomotive engine block weighs closer to 10,000 kilograms. That is 50 times the mass. The thermal energy required to keep that much metal above operating temperature in sub-zero conditions overnight is not a plug-in cable you run from a wall socket. It is an industrial heating system. Infrastructure that most rail yards, especially the older ones threading through the interior of the continent, simply do not have. And even in yards that do have some shore power capability, the number of locomotives needing simultaneous heat on a cold January night far exceeds what the existing electrical grid connection can support. So the engine stays running, and it runs at what is called low idle, roughly 4 gallons of diesel per hour, all night, every single winter night. 4 gallons an hour sounds like waste. It looks like waste. Standing next to a parked locomotive at 2 in the morning, with no train attached and no crew in sight, it genuinely feels like waste. It simply is not. Here's the cost calculation that railroads run, and have been running for decades. A single locomotive engine overhaul, just the overhaul, not a full replacement, runs between $200,000 and $400,000. One engine, one rebuild, and cold start wear accelerates the interval between rebuilds significantly. A locomotive that idles through its winters and gets started warm every time reaches its scheduled overhaul on schedule. A locomotive that gets cold started repeatedly arrives at that same overhaul thousands of miles early and in measurably worse condition. The math is not close. 4 gallons an hour is cheap, catastrophically cheap, compared to the alternative. But even that calculation misses the bigger operational reality, because a locomotive that will not start in the morning is not just a maintenance problem. It is a network problem. A single freight locomotive on a transcontinental corridor might be scheduled to pull a unit grain train out of a Wyoming rail yard at 5:45 in the morning, hand off to a fresh crew in Nebraska, and arrive at a grain elevator in Illinois by the following evening. That train is part of a tightly sequenced operation. The track slot it occupies was reserved days in advance. The relief crew at the Nebraska handoff point is already staged and waiting. The elevator on the receiving end has its inbound unloading capacity scheduled around that specific arrival window. A locomotive that will not start at 5:45 does not just delay one train. It delays the crew. It delays the track slot. It holds a second train behind it on the same main line. The elevator adjusts its unloading schedule. The cargo ship waiting at the Gulf port for that grain adjusts its own departure window further downstream. One failed cold start, one frozen fuel line, one cracked coolant fitting discovered at 4 in the morning, and you have a cascading delay that does not fully resolve for 18 to 24 hours across a network that runs on margins measured in minutes. Railroads are not sentimental about fuel costs. They are some of the most operationally precise logistics systems ever built. Union Pacific alone operates roughly 7,000 locomotives across a network, covering more than 32,000 route miles. If idling overnight were genuinely wasteful at the systems level, they would have engineered past it decades ago. The fact that every major North American railroad, Union Pacific, BNSF, CSX, Norfolk Southern still idles locomotives as standard practice is not tradition for its own sake. It is the result of continuous cost modeling run against every available alternative, year after year. And it keeps producing the same answer. And those alternatives have been tried seriously. Automated shutdown and restart systems exist on many modern locomotives. They shut the engine down after a set period of inactivity and restart it automatically before the coolant temperature drops to a dangerous threshold. They work in moderate climates on newer locomotive models, when every sensor and relay functions correctly. In extreme cold, on older motive power, they introduce a serious new failure mode. The automated restart fails. Now you do not have a cold locomotive. You have a cold locomotive with a depleted battery bank and a maintenance crew on the phone at 4 in the morning, trying to find a ground power unit somewhere in a darkened yard. And so the idle keeps running. Night after night, yard after yard. There is a number attached to all of this that sounds alarming until you stack it against everything else. A locomotive at low idle burns roughly 4 gallons of diesel per hour. Across an 8-hour overnight window, that is 32 gallons per locomotive. Across a fleet of several thousand locomotives, that is a real and closely tracked fuel expense. Railroads model it every budget cycle. And they keep doing it. Because 32 gallons of diesel costs roughly $120 at current prices. A single-cylinder liner replacement on a 16-cylinder locomotive engine costs more than that figure alone. A cracked engine block from a freeze event can mean weeks out of service and repair bills well into the 6 figures. The overnight idle is not really a fuel cost. It is an insurance premium on a 220-ton asset that keeps an entire freight corridor moving. A remarkably cheap one. Measured against what it is protecting, the locomotive idling in that yard tonight was probably built in the 1980s or 1990s. Some of them are older still. North American railroads run their motive power for 30, 40, sometimes 50 years before retirement. That machine has been idling through winters for decades. The engineering logic that keeps it running at 3 in the morning was settled long before most of its current operators were born, and it remains correct. Modern Tier 4 emissions-compliant locomotives have better cold start tolerances than their predecessors. Battery tender systems are improving year on year. A growing number of rail yards in milder climates now have shore power hookups capable of handling the full thermal load. The industry is moving, deliberately and carefully, toward a future where the overnight idle is no longer the automatic default answer, but deliberately is the operative word. Changing the default requires upgrading locomotive onboard control systems, rebuilding yard electrical infrastructure across thousands of locations, and shifting deeply embedded operational habits that have been validated by decades of real-world performance data across some of the harshest operating environments on the continent. That is not a fast process. It is a careful one. And until that infrastructure catches up with the ambition, the engines run. So the next time you hear that low, steady thunder rolling out of a rail yard at midnight, you are not listening to carelessness. You are listening to a machine being kept alive. Warm oil circulating through a 16-cylinder block, fuel lines held above the temperature where chemistry turns against you, air brake reservoirs holding pressure, a 220-ton piece of equipment that a crew needs ready at 5:45 sharp, because a grain train in Wyoming and an elevator in Illinois are both counting on it. That is not waste. That is engineering. And the next time someone tells you that idling locomotive is pointless, you now know exactly why it is not. And speaking of locomotives managing forces that should, by every reasonable intuition, be completely uncontrollable, the way a fully loaded freight train holds itself on a long mountain descent without destroying its brakes or losing the entire consist is one of the most counterintuitive pieces of mechanical physics in the transportation world. The solution involves converting kinetic energy in a way that has nothing to do with friction pads or wheel pressure. And the consequences of getting it wrong happen very fast indeed. If the hidden systems inside